Today, let's look at section 1.3, which is exponential functions. So an exponential function is one where the variable x is up here as an exponent. So the definition says that we're going to let a be a positive real number that's not 1. If a happened to equal 1, you'd have 1 to the x power, which of course is always equal to 1. And so you have a horizontal line and just be y equals 1. So that is not allowed here. So as long as a is not 1, but it's a positive real number, then this equation here is our equation for an exponential function. And of course, a is the base. When we have an exponential function, the domain is all real numbers. You're allowed to plug in anything for x. The range, because you're taking a positive value, remember a is a positive number, and then we're going to raise that to a power. The range, the y values, are going to be greater than 0. So we actually have a horizontal asymptote at 0. If a is greater than 1, then we have what's called exponential growth. So if that base is greater than 1, we have exponential growth. If a is between 0 and 1, remember it has to be positive, but if a is between 0 and 1, then we have exponential decay. And I included a couple graphs here to show. This first graph shows exponential growth. You can see the x-axis at y equals 0 is our asymptote there. That's the exponential growth function. Of course, it continues up there and continues to the left, but never quite reaches that x-axis. And then the exponential decay function is really just a reflection over the y-axis. Again, the x-axis is your asymptote. Your domain is all real numbers. Just to quickly go back through, you've seen these exponent rules multiple times, probably Algebra 1, Algebra 2, maybe even a little bit of pre-calculus, and even before that probably. So this should be pretty straightforward. But if you are multiplying and you have the same base, and that's the key, if you have the same base, then you're allowed to add those exponents. So we'd have a to the x plus y power. In the second one, again, we have the same base. They both have a base a, so then we go a to the x minus y power. So you take the exponent in the numerator and subtract the exponent in the denominator. Then in this third one here, we've got a to the x to the y power, and in this case, we then multiply those exponents, so it'd be a to the x times y power. And then if we have a times b to the x power, then it kind of looks like distributing. That's the way students think of it. It's a to the x times b to the x. You are allowed to do that. Likewise, if we have division, so if we have a divided by b to the x, as we see in that next one, then again I can rewrite that as a to the x divided by b to the x. Now I want to take a moment to talk about these two here. Those are rules that we can use. Where students run into trouble is when they see something like x plus y to the second power. And they try to apply one of these rules and they say x squared plus y squared. And of course that's not correct. That's not equal. When you have x plus y squared, that really means x plus y times another x plus y. And you need to distribute or FOIL, what have you, to get your answer. So in this case, you'd actually get x squared plus 2xy plus y squared. And you probably already knew that. But the same thing goes when you get bigger and bigger powers. If you have x plus y cubed, of course, that means you have 3 separate parentheses, or you may have learned at one point how to do binomial expansion. And that's not really the purpose of what we're talking about here. But I wanted to mention that the two rules here on the left, while they do work when you have multiplication and division, they do not work when you have adding or subtracting. You can't just distribute that power. All right, moving on then, if I have a to the negative x power, well, that's the same thing as 1 over a to the positive x power. And then the last one that we have here on this slide, if you have 1 over x power, well, that means the x root, the principal root of a. All right, well, we see exponential functions in real-world applications, and one of those is a chemistry example. is talking about half-lives. If you look at this example here, it talks about radioactive decay, that we have some substances that are radioactive, and that just means that they break down with a process. They emit energy. It could be like gamma radiation. They emit energy, and the substance changes. And so we often talk about what's called a half-life, and a half-life is actually an amount of time. It's the amount of time it takes for half of the substance to change from its original radioactive form to a more stable state by emitting energy. So let's suppose the half-life, I'm looking at example 4 here now, let's suppose the half-life of a certain substance that's radioactive is 20 days, and that there are 5 grams present initially. When will there be only 1 gram of the substance remaining? Now when we do a problem like this, I'm going to modify that exponential function. On the previous slide, or 2 slides ago, we talked about a to the x power. But we're going to have a starting amount here as well, so let's modify this here, y equals, and if we want to keep using a as our base, we need another letter in front. And I want to say that the book uses k. It doesn't really matter what choice of letter that we use, but the important part to know is that this value here is your initial amount, and a, or whatever letter you choose, I think in Algebra 2 we would use b, but it doesn't really matter. A is your growth rate, your multiplier. And in this problem, and x, that's your number of time periods that have gone by. So in this problem, we know that this substance, we start out with 5 grams of it, and we know that it has a half-life of 20 days. So if I want to write an equation for that, y equals, k would be 5 grams, and then my multiplier here would actually be 1/2. But the half-life, we know that that's the multiplier. That's growth. Is not really growth. We're decaying. And remember from 2 slides ago also, when that base is less than 1, then we have exponential decay. So because it's between 0 and 1, that's exponential decay. And we raise that to the x power. Now in this particular equation, x is not going to be the number of days, but it's going to be the number of 20-day periods. And the reason for that, we're told in the problem that it takes 20 days for a half-life. So every 20 days, we should multiply by this 1/2 once. So if I had 20 days go by, I would not plug in 20 for x, because then I would have 1/2 to the 20th power. I don't want that. After 20 days, it should be cut exactly in half, so we should multiply 5 by 1/2, which would mean I would need to plug in a 1 in there for x. All right, so let's finish the question. It asks, when will there only be 1 gram of the substance remaining? Which means I need to plug in 1 somewhere. I'm actually going to plug it in for y and for kind of my final amount of the substance, or at least that's when I want to freeze the time, press stop, pause in the stopwatch there, and check the amount of substance. So let's say we have 1 gram of it. We start with 5 grams of it, and then we have 1/2 to the x power. Now, to solve that, I'm going to divide both sides by 5. So I get 1/5 equals 1/2 to the x power. Now, it's at this point that, technically the book has not talked about logarithms, but it's not like you guys haven't already learned and should know those well. And so let me go through a couple options. How do you solve something like this? Well, you could certainly do guess and check. You could plug in numbers for x until that works. Your book talks about graphing. So you could graph this right-hand side. On your graphing calculator, you could go y equals 1/2 to the x. And you could graph that and like trace, and you want the y value to equal this 1/5. So you could trace until you found 1/5 and then use that as an x value. There's lots of ways that you could do it. We're going to talk about logs in a later video. We might as well just do it now because it's not like I'm letting out some big secret here. So if you have 1/5, because that's really the method we would use to solve this, equals 1/2 to the x. Now I'm just going to take the log of both sides. So maybe I would take the log base 10. So I'd have the log of 1/5 equals the log of 1/2 to the x power. And if you remember from our log rules, and we'll revisit this in a later video, I can take that exponent and bring it down in front. That's the reason for taking the log of both sides. So now I have x times the log of 1/2. And on this side I have the log of 1/5. And so now to finish this, I could divide both sides by the log of 1/2. And then I could use my calculator to approximate that value, right? So I have x is approximately, and I would need to then go to my graphing calculator. I've got mine here. If I go the log of 1/5, which is 0.2, divided by the log of 1/2, which is 0.5, and I get approximately 2.32. 2.32. Now, we got to be careful. 2.32 what? Well, in this problem, x stood for the number of 20-day periods. So we have a little more than 2 20-day periods, which means we're going to be somewhat over 40 days. So if I take 2.32 approximately and multiply that by 20, I'll get my approximate number of days that have gone on. So in fact, if I keep that whole decimal, so my decimal was 2.3219285.095. Take the whole thing that you got in your calculator, multiply that by 20, I get roughly 46.4 days. Now again, you could do this problem with graphing, you could do it with guess and check. There's a variety of ways to do it, but that's using logarithms. And this is really the equation that I just talked about in the previous slide. Y equals k times a to the x power. Again, k is your initial amount, a is your multiplier. And like we talked about, if a is greater than 1, you have exponential growth. And if a is between 0 and 1, you have exponential decay. Now, this equation here, you've seen before, PERT. We use that for whenever you have a continuously compounding situation. Again, just like in the last equation we looked at, P, this is your initial amount. And remember, E is a number that's on your calculator. It's an irrational number, approximately 2.718, right? But of course it goes on and on forever. R is your rate as a decimal. And then T is your time. So for our last slide, let's say the population of Knoxville is 500,000 and it's increasing at a rate of 3.75% per year. Approximately when will the population reach 1 million? It doesn't tell us to use the continuously compounding formula, so I guess I'm not going to. I'm going to use the y equals k times a to the x power. So I would put in 500,000 for the initial amount. My multiplier, let's see, I have 3.75% growth, so that would be 0.0375 as a decimal. But of course, you add 1 so that we make sure you have growth, right? The 1 is the keeping the original population, and the 0.0375 is the growth. So my multiplier here will be 1.0375 raised to the x. That's my equation here. Now we want to know when will the population reach 1 million. So I would put in 1 million for y. And much like that last problem, I'm going to solve this for x. So I would start out by dividing both sides by 500,000, and when I do that, I end up with 2 on the left-hand side, and I have 1.0375 to the x. And just like the last problem, you could do this by graphing, by guess and check. I'm just going to go ahead and take the log of both sides. So if I take the log base 10 of 2 and the log base 10 of 1.0375 to the x, that allows me to bring that x down in front. And then lastly, just divide both sides by that log of 1.0375, and you'll have your approximation for x. And again, you can put that on your calculator. That'll give me an approximation for x. Now let's just take a quick peek in this problem. What is x standing for? Because it was a 3.75% growth per year, that tells me that x will indeed be the number of years. And that's it for section 1.3.